So now we come to the last part of Lecture 1, how to read a research paper. So how people read is clearly a personal thing. This is a little quote from Emily Dickinson. The way she reads a letter, the way I read a letter, this, 'tis first I lock the door, and push it with my fingers next, to transport it, be sure. And then I go the farthest off to counteract a knock, then draw my little letter forth and softly pick its lock. She's talking about how she reads a letter, has intimate things she wants to be in her own private space. But you're going to read for academic reasons, for other things. I'm going to talk to you a little bit about my techniques, my recommendations for you, but obviously you have your own style. You can develop your own way of reading, and if you want to go to the farthest back of your room and lock the door to read your papers so you have some peace and quiet and kids can't get to you, that's okay too. So why do we read? We read really to learn to do research, to learn to think about critically about the quality of research and research papers. This is really important when you're beginning. Someone else is going to be thinking critically about your own work. They're going to be reviewing your work, and therefore you need to think, how will they think about it? And the only way to really get that is to have gone through lots of papers and have an idea of how people present stuff, how they tell their story, and what makes good work. And also in any discipline, you want to be able to identify what's a fad and what's a lasting idea and learn to tell the difference. So there's some reasons to think critically about the research papers you're doing it. After you've already learned how to do both of those things, you're still going to keep reading because it's the way you gain perspective, the way you gain knowledge about other problems, and the way you keep up to date. As we've already talked about, research is at and advancing the state of the art. If you don't know what's the state of the art, you can't be doing good research, so you have to be continually keeping up. But as we go through reading, some of the key issues you want to deal with are, what are the right questions to ask? What are the right questions to answer? And as you read lots of papers, you'll get more ideas of the questions they asked and the questions they answered. The ones they've answered, well, obviously you're not going to want to answer those questions, but you might be able to draw analogies as you read to do this. So research papers are the primary form in which research results are disseminated in computer science. There are also talks at conferences, but very rarely in computer science are those not accompanied by papers. In some other fields, there will be talks at conferences where they might have an abstract but no paper to go with it, and they save the papers for journals. But computer science as a field is somewhat unique in that we have such a strong dominance of conferences. Conference papers tend to be shorter, 6 pages, 8 papers. Some only have 4. Journals tend to be longer, 10, 12, 20 papers. They're often a complete version of a conference paper, so a lot of experiments and things were added. More often, they're actually a combination of multiple conference papers put together. Journal papers may come out 7 years after the conference, several years after the conference. They might combine these multiple papers and provide a broader view, which still gives them some real value, especially when you're getting into the field. So as we go through this class, you're going to be reading journal papers because they provide a sort of a broader and more in-depth picture, and then conference papers because they're the most up-to-date thing. You have to be a little careful. Some people will do conference papers followed by journal papers. Others, myself included, tend to view the top conferences as a sufficient final destination for it. And so many of my top papers that have shown up in conferences do not have a journal version. I tend to go journal or conference, not both. Some people will do both, in which case you quickly figure it out and you won't read the second paper very much. Peer review is the cornerstone of scientific publishing. It's what helps us assess the quality, and the impact matters. So you want to look for places that have good peer reviewing. We'll talk about that again when we discuss writing, and this is talking about how we'll look at the peer review process and plan for it. But right now we're going to look about reading, and this reading is for you. How do you become a better researcher through reading? So the way I present it, you're going to have a 5-path method for reading a CS research paper. This is actually based on some work by Kejla, and there's various other people who have done similar techniques. Whether or not it's 5, 4, or 6, you can make some variations, but you'll get the basic idea. In this class, we're going to use these 5. Actually, we're going to use the first 4 of the 5 most of the time. So before we get into pass 1, I want to justify it a little bit. We've already talked a little bit about searching. And so if you know the keywords, you now have the tools to go in and find papers that have those keywords. You even have some ways of using, once you have a paper, to find other papers that are related to it. But you may not simply understand the terminology for what to find. even if you've been working for a long time like I have, every time there's a new subfield, I might not have the lexicon nailed down, so I won't do a good job finding it by keyword searching. Furthermore, that won't let me keep up with things I don't even know about because I'm not searching for them. It's very important for you to keep aware, especially when you're starting out. So you need to just look through stuff. And stuff is a lot. You need to be able to consider hundreds of papers per year. Last week, I did 15 papers last week. 6 of them were published, 10 of them were not. They're papers for being reviewed, but that's a pretty normal week for me to be looking at tens of papers, 10 to 20 papers a week at different levels. Big conferences have somewhere between 200 and 700 papers in them. And if you take 300 papers in 10 a week, you're at 30 weeks. You're half a year just to keep up. So you're going to have to do more than 10 for the big conferences. And journals, the top journals in my field, there's 3 of them. They publish around 400 papers a year. So with 2 to 3 big conferences per year, plus 4 or 5 Tier 1 journals and 4 or 5 Tier 2 journals, there's a lot of stuff to consider in your field. Searching is tempting because it seems to limit your work, but it's not enough. You really do have to browse to keep up. You're going to want to keep a reading list, a library and Google Scholar or whatever. You're going to add to it frequently. So let's talk about the browse. The browse is a very useful thing, and one of the reasons computer science conferences are popular is because they also provide you a different way of browsing, which is if you attend, you can go to a bunch of talks and browse without having to read them. But in general, you browse will allow you to go through hundreds or thousands of papers a year. And the real goal of the browse is to help you be efficient, but also be aware. You're going to browse through many, many papers to see what's interesting and relevant. One approach is to really pretty much just first scan the abstract, read the figures and captions. This is a 1 or 2 minute gut check based on the content. And if after reading the abstract and looking at the figures and captions, reading the comic version of it, you can't tell that this is good or it's relevant or interesting, then you're done. You're done your browse. Move on to the next paper. You might also be doing a venue check and an author check. If you're browsing by having a conference venue in front of you or a journal, then that's not important. You might also do an author check. Very often when I'm browsing, I will skip over things literally just based on the title. If the title doesn't sound relevant or doesn't sound like I have to read the abstract to figure it out, and the author is not somebody that I know of, I might skip over it. Papers and places by people or that cite stuff you already know are relevant are more likely to be relevant. So I'll also sometimes page to the end and see what they're citing and see if that's relevant. And if it is, then I'll go ahead and browse it. In the beginning, it's really good to err on the side of being positive. That is, add it to the reading list, even if it's only slightly positive. If you don't know, you might want to look a little bit deeper at it, right, than spending a minute to decide that it's not relevant and then missing something important. That's the browse. And you should be able to browse. If you're doing a minute or 2 minute, that means you can do 30 papers in 15 minutes at 2 minutes each. Sounds like a lot, and it'll take some practice for you to get there, but it's actually important to practice and not get sucked into the paper so much that you keep reading it. And if you sit down with a large volume with hundreds of papers in it, it's easier to keep that in check because you're sort of timing yourself as you got to go through lots of these. The next layer of reading your paper is the skim. So if the browse was positive, it's time to skim positively. And realistically, I view the browse as building a reading list. The skim is your next pass through the reading list. You don't browse and then instantly skim. You browse for a while, skim later. In the skim, first rule is you believe everything and assume it's all true. Everything. A little bit like improv. You just accept the world as it's being presented to you, assume it's all true. And given that, decide if the paper is actually interesting and worthy of more explanation. You'll be surprised how many papers fail at this stage. Even if you believe everything, you end up saying, who cares? And if you say who cares, then it leaves the skim, it goes from the skim pile to the dead pile. If after you've done the skim, you believed everything, and the skim, you actually now try and read each section of the paper, although you're going to be reading very quickly. You believe everything. You don't check the math. You don't even necessarily spend any time on the equations. You're going through it pretty quickly. And then you try and summarize the paper in 2 or 3 sentences. And if you, in 2 or 3 sentences, can't say what is the problem that is addressed, what is new about the paper solution, and how significant was the experiment theory, you probably skimmed too lightly. You need to go back and answer those questions. If you have too many ideas to express in only 2 or 3 sentences, you may have gone too deep. So you should be able to skim a paper in 5 to 10 minutes. So you don't know everything, you haven't analyzed everything, but in 5 to 10 minutes you can get a pretty good idea this paper is worthwhile. Notice how this is 3 to 5 times the length of our browse. So we spend a little bit more time on the paper and go through that. You could imagine trying to skim every paper, but when you have hundreds, the difference between a minute or two and 5 to 10 minutes is big. So you want to balance that out and not skim too many papers. Sometimes I also call the skim, the browse plus the skim together is a scan, because I've actually looked at the paper twice. So after that scan, you should be able to answer what I call the 6 C's. Category. This is really simple. What type of paper is it? Context. What other papers are related to, and how's that related to your work? This is tough in the beginning because you don't have that many papers are related to, but very often when I've scanned a paper or skimmed a paper, I can quickly say, here it's related to these 5 or 6 other papers. Part of that can be easy because they might be referenced. But even if they're not, you should be able to do that. What are the main contributions? A good paper will have made this really easy. There'll be a place where they told you what the main contributions are, but your idea of the main contributions might be different from theirs. Is it credible? Now, you weren't supposed to be analyzing it deeply, but does it appear to have any credibility? If you're reading through it and there doesn't seem to be any experimentations, and it's a comparison, then it might need experiments, then it might not be credible at all. And do you care? The whose care system. Even if everything is valid, will anyone care? Will it change anything in the world? Does it care for you? And then the last one is cost. Cost for you. How much time and effort will it cost you to read it carefully? And now you have to take those 6 C's and decide what happens to this paper. Does it go onto your read more deeply list? Or does it go to the who cares list? I've looked at it. I'll keep my 3 sentences that I wrote down about it in my bibliography in case I have to go back to it again. But otherwise, it's done. So after this, these I would actually call neither of these really reading a paper. So when I say I read 10 to 15 papers a week, that's not these. That's how many papers I browse or skim. It's probably 3 times that number in terms of what you need to do to keep up every week. But you're going to read at the next level more. So a critical read is the 3rd pass. For me, a critical read is 20 minutes to an hour. It depends. But for you, I'm going to say it's an hour. Depends on your level of background, how many related papers you've read. Sometimes you can go through them faster. So at about an hour, you don't want to be doing too many of these. If it's half an hour, you can do 10. That's 5 hours a week. You can probably support that. If it's taking you 3 hours, you're probably going too long at this level. But when you get started, they might take you more than 2 or 3 hours because you have to understand the background. So at this critical read, you're going to read carefully, but you're going to ignore the details in the sense that you're not going to check proofs, for example. You're going to believe the math, but you are going to be checking some things about it. So you want to note assumptions and question them. You want to analyze experiments and conclusions. You want to make sure that those experiments are supporting the conclusions they're drawing from them. You want to analyze the figures, diagrams, illustrations, and graphs. Are they properly labeled? Are there error bars? Are they actually showing you good science as it's being done? Are you going to, as you're doing this, you're going to mark relevant unread references. So as you're reading through this paper, you're saying, oh, here's the things I don't understand. I need to understand them. Now, to understand all the math might be even deeper. So at a certain level, you're not trying to say, I don't understand this integral. I have to go read about integrals. You don't want to go down a rabbit hole as you're doing this. But you should be looking at them. So as you go through this critical pass, you should be able to summarize the main thrusts and point out the likely weaknesses in the assumptions, methodologies, and/or experiments. So as you're doing this, right, there's a bunch of questions you want to ask yourself. So I'm going to go through a couple of lists of these questions to make it a little bit clearer. I said note any assumptions and question them, analyze it. Well, let's talk about some of the questions you should be trying to make sure you get as you do this critical read. So if you're reading critically, the first thing is you have to understand the problem. If you don't understand the problem you're solving, the rest of the paper isn't going to make sense. Some authors make this really easy. Sometimes it's really tough. Understanding the problem also means understanding what's not the problem. What are the related things that it's not? Understand the proposed solution. At a high level, you should be able to describe pretty quickly this is what the solution is about. And related to that, you then want to be able to think about what are the competitive approaches and designs. This may be in the paper. Very often papers will have sections where they talk about related work, and they'll tell you some of those. But as you're reading critically, you want to think about what are the approaches you know about that they didn't talk about, because that's equally important in terms of being critical and understanding what the paper is and what's the relationship. Understand their evaluation methodology. They've made some claims, right? It's not just a proposed solution. They've proposed that they've advanced the art in some way. Hopefully there's some comparison to the state of the art. And then you have to understand what's the evaluation methodology and what's underlying that. We'll spend some time later in the semester thinking about or talking about statistical analysis and how you do experiments. You're going to want to think about these from that point of view as well. Okay. In this read, you're evaluating the paper's claims. You don't want to assume the paper is correct, even if it's been published in a prestigious peer-reviewed venue. I've seen plenty of papers, in fact, award-winning papers sometimes, that are simply wrong. They've made an assumption that isn't consistent with what the paper's about. And it only takes one assumption and then everything else doesn't follow. So you want to be careful as you're checking it for correctness. This can mean checking some of the math. At this point, that's a balance. If you understand the math, and checking it is important. And I'll go through a little bit more, some examples of that are pretty easy to do as you're going through this. The critical read may require backtracking and fact-checking. You need to jump around and evaluate the claims related to the paper. This read is definitely not in order. In fact, none of the reads we've done necessarily are in order. The browse and the skim might also skip large parts of the paper. Here you're probably reading it all, but you might have to go back and check, oh, is this what they said? When you're doing reviews, this is the kind of stuff you go back and forth all the time. So when you're reading these sources critically, you want to also check what they've cited. So have they evaluated or cited the right material? Have they gotten all that together? You want to ask some credentials about the reputation of the author and the place of publication. If you've heard of this author, you might quickly assume that what they're going to say is more likely to be true. If you don't know who they are and they're saying more grand things, then you want to be a little more careful about checking what that is. You might ask yourself, what do you think is the writer's purpose and the audience whom the author is addressing? At one level, the author might be writing to you as the reviewer, they're writing to the general audience, but sometimes the authors have other purposes, and if you can figure out what those are, it might help you understand why the paper's approaching the paper from a particular point of view. You want to ask questions about the ideas you read. So, an easy way to do this is to highlight some of the sections, write annotations to the margins, or keep a reading journal. And if you get a sense of doubt, or you're unsure about anything, make a note of what troubles you. You'd be surprised how often after you start digging, your first gut instinct was actually spot on, but it takes you a while to figure out why and nail that down. So when you're doing this, at a minimum, I tend to read online, so I'll just grab a highlighter and highlight sections that'll remind me to go back and look at them in more detail. I don't want to get bogged down too much when I'm doing the critical read. There's a lot of things to think about. So anything that just bothers me a little bit, highlight it, come back to it. Okay. Be on the lookout for assumptions that may be faulty. In fact, the reason I said not to check all the math is there's lots of times when the math will be perfectly fine. It'll always be an assumption that kills the math. That is, there's some underlying assumption that's probably wrong. Okay, so, and look for biases. If you're reading an article on computer-aided homeschooling and the writer favors homeschooling because it avoids subjecting students to violence in the school, the unstated and probably untrue assumption is that all schools are violent places. Something like that can easily go by when you're not paying enough attention because they say, well, you want to avoid school violence. And of course, violence is bad, but the question is, how much violence is there? So there's an unstated assumption that you can then come back and question in terms of what's really going on. You want to make sure that the writer's evidence is adequate and accurate. If the example is the writer is talking about generalizations and said something about Chinese students based on a study of only 10, you have cause to challenge generalization as resting on inadequate evidence. 10 is not a big enough study to draw much of a conclusion about anything that involves people. 10 is probably statistically not significant for lots of problems. So you want to be very careful how they're looking at it. And if the evidence is adequate. When we talk about statistics and stuff, we'll come back to that in more detail. Note how the writer uses their languages. That'll often give you a clue in terms of what they're doing in terms of biases. Does a writer use certain things with positive or negative connotations, signaling the value the writer holds? Are they flamboyantly denigrating and dismissing views of others with phrases such as a ridiculous notion or laughably inept? Writers that use that are being ascientific. Those phrases generally don't belong inside a scientific paper. And if they're doing that, you then can question a lot of the rest of their scientific processes, because that's just not the way we do good science. Related, be very alert for sweeping generalizations, biases, and prejudice. Things like women want to stay at home and have children, men love to spend Sundays watching football. Again, these are overgeneralizations, and once you start questioning an author because they're overgeneralizing, you probably want to question lots of what they say, and you have to dig deeper to see, is what the other things are saying sustainable. So coming back to these critical questions, is the problem carefully stated or formulated, or is it some vague paragraph that gives you an idea what the problem is, but they never formalize it? Formalized problems are easier to actually analyze and generally more valuable within a paper. Is it a really meaningful problem area? Imagine that it was solved. What difference would it make to the world? If it isn't, maybe no one cares. There are plenty of papers that invent an academic problem or a problem that is of interest, but isn't actually a model of the real world. Okay. Related to that, is it the right problem? And this is a question of the formulation versus the description. If they have a high-level description talking about a real-world problem, but then their formulation simplifies it to the point where it's not a good model, then it's not a particularly good problem. So if you make an assumption, so if you're talking about a system that's trying to inspect chickens, and then in the formalized part of the problem, you say assume a spherical chicken. Chickens aren't spheres. The problem is no longer the right problem. It's no longer relevant. Can you make a list of assumptions, explicit and more importantly implicit, about the problem itself, not about the solution, about the problem? Are they making realistic assumptions about what the world is and what the model that you're trying to deal with is? So, for example, if you're dealing with a computer system, you can make explicit things about the way parallelism is done, but you can have implicit assumptions because you didn't talk about how the memory system works, or you assume that the memory system has large caches or something so that there's no interference between. Whatever those are important assumptions about the problem that you have to try and figure out what they are. What, if anything, is novel about the problem formulation? Lots of fields are very interested in, and people care a lot about novel problem formulations, because that allows us to solve something that's not been solved before. Sometimes the novelty is an important novelty. Sometimes it's a novel but not particularly novel element or not realistic element. You want to understand what those are. And what is known, what well-known problems are related to the same problem that you're looking at? This is useful because if there's a related problem, then some of its techniques may or may not apply, and maybe that should have been part of the point of comparison. And all of these, so notice all of these are really critical questions about the problem itself. Because if we don't have the right problem, or if the problem's not novel or important, then a lot of the rest of the paper doesn't matter. Very often when I'm reading a paper critically, I've passed through the scan paper, but as I'm reading critically in the section, if I decide that the problem is an unrealistic problem, then most of the rest of the paper probably doesn't matter, and I might stop at this point, saving myself some time. When you've found related problems, you might also want to ask, are there simple solutions the authors don't seem to have considered? Sometimes it's surprising how often there's an already existing simple solution and the authors want to invent something much more complex. So now we move on to the technique. Can you make a list of assumptions, implicit and more importantly, implicit about the technique? This is one of the places where you do want to check the math. As I said, most people don't make too many mistakes when they're doing the mathematical manipulation. By the time they put it in the paper, they've probably checked it, but they haven't always checked their assumptions. So every time there's a divide, you want to make sure that the divide couldn't be a divide by zero, because that may make the algorithm broken. And if it's a divide and it's not by zero, but it's by 10 to the minus 37, maybe the algorithm blows up. So there's the potential for problems. What are their matrix operations? What happens if the matrix is singular if they're doing matrix operations or functional inversions? If they're doing minimization or maximization, is there a reason to believe that there's a unique minima or maxima? They won't get stuck in a local one. Is there a reason to believe that a minima even exists? And along the way, are the assumptions that they're making, are they justified? Sometimes you can prove that things will have a local minima, a global minima as their local minima, and other times you just live with the fact that it's just going to be a local minima, and they've pointed that out. The more honest the author is about some of the limitations, the more you can sort of move quickly through the section. If they're not, then you want to figure out what those limitations are. There's lots of limitations that people are stated implicitly in terms of the type of noise used, how the data is generated, and whatever. What are the limitations of the solution as opposed to the technique, including limitations the authors may or may not have clearly admitted. So this is now thinking at it as a solution from the problem point of view. Sometimes there are limitations that the solution is only going to be meaningful for big sizes or for small sizes. So if they're talking about things that have an approximation along the way, what those limitations apply on the solution space and the problem space that go along with it, so that you can understand how those work out. Is the logic of the paper clear, justifiable, given the assumptions, or is there a flaw in the reasoning? So if the paper, for example, has to assume that some value is not zero, but the value can easily be zero, then there's maybe a minor flaw in the reasoning. If the system has to assume that the matrix is non-singular, but the number of rows is always less than the number of columns, so the matrix isn't even square, then there's a broader flaw in the reasoning. You have to figure out what's going on. You'd be surprised how often this kind of thing can happen. If they are right, do the pieces of the work fit together? Sometimes you'll have something that is talking about an optimization in one element that's, for example, assuming Gaussian noise, and someplace else you're assuming uniform. Right? Those two are not consistent. You can't have the same data have two different kinds of noise at the same time. Has the right theorem been proven? So if they have a theorem, is it actually directly related to what they're doing, or is it assuming something that sounds related but isn't quite on the mark for this problem? And are the theorems logically supported? Are the proofs given, or are they cited? And if they're cited, how credible a source? Sometimes people cite something slightly out of context, coming back to is it the right theorem, and they've misinterpreted or misstated what that is. The number of times I've seen people misusing the central limit theorem to justify Gaussian assumptions is large. Right? People are citing something, but it isn't quite the right way of doing it. If the authors present data supporting their arguments, did they gather the right data to substantiate their argument? Did they appear to gather it in the correct manner? We'll spend lots of time later in the semester looking at this in some more detail, but if they're talking about something very general, but they only tested it on college students that they could get in the lab for human factors, that's not a broad statement. So there's a disconnect between what they said and what they collected. Doesn't mean it's completely wrong. It might just mean they need to greatly restrict what they're saying they can do in terms of, is it the right data for their arguments. We'll talk again later in the semester. Do they have enough data to make a statistically sound decision? In general, if they only have 20 or 30 points of data, they probably don't have a good decision unless the problem is very simple. As it gets to more complicated models, it takes more and more data. So do they interpret the data in a reasonable manner? Would other data be more compelling? This is a little bit creative, but is there a reason they didn't do something? So if they've done a comparison with an algorithm, but that algorithm is 3 years old, why didn't they compare with something more recent? Some of the times they haven't compared with more recent because they couldn't get it, but other times maybe because there's some underlying assumption that makes it inconsistent or that would make them look bad. Did they compare with the actual state-of-the-art performance? Now this is tricky because it means you know what is the actual state-of-the-art. So one of the places where keeping abreast of what's going on is important. Although this is also something where if you're really trying to check it out, you can often go searching. If you don't know the particular data set, you can quickly go into Google Scholar and search for the state-of-the-art results, windowing it on the last couple of years and looking for the performance against that particular data set and get an idea for where are they. This is a classic one that causes a problem in areas doing anything with machine learning or training and testing. Was the same data used for training and testing? That's a big no-no. If I train on the data and test on the same data, I can always do significantly better, but there's no realistic world problems for which training and testing data are exactly the same or have a large overlap. Related, but sometimes more subtle, is were the parameters selected on the test results? So if I basically have some free parameters, or what we call hyperparameters, and I run lots of tests, and I choose out of these the parameters that did best in the test result, well, that's also unrealistic, because if I ever wanted to apply this algorithm on another problem, I wouldn't have the test results to know how to do that comparison. Parameters should be selected on the training data, not on the test data, the same as other uses. Finally, when you get to the end of the paper, you want to ask yourself, what really were the results? And did they do what they set out to do? Sometimes the beginning of a paper sets you off in a direction that gets you excited, but along the way you find they didn't actually solve that problem. They solved something that sounds like that problem or something related to it, but they didn't quite get there. Which is okay, you just have to put it in context. What did they really do? And you should definitely be able to answer at the end of your critical on what dimension or dimensions did they advance the state of the art. If you can't answer that, then there's a problem with the paper because it should make it pretty clear how they advanced. Do they have to advance on everything? No, they just have to have some dimensions where they do better. As you're reading, you might also be asking yourself, have the authors been cutting corners, intentionally or unintentionally? Did they sort of do some shoddy experiments where they could have done better and didn't? Not the end of the paper, but you want to understand how to put everything else in context. An important and growingly important question is, would the results be reproducible? If as you're reading this, you don't see how you could ever implement this because there's missing parameters or missing data, then this paper has less value for you because no one else can reproduce it. It's not uncommon for companies to have papers where the data they've used can never be released, or where you've done IRB stuff where your data can't be released. That just means that if the data is going to be, if the results are going to be reproducible, they have to find some other set, which might be public, where they can test it on that you could also be able to get access to, or find some way to abstract the data so they can release results that will be reproducible for comparisons. Are there any problematic issues in their experimental setup? Things that when you look at this are going to cause problems if you were to try and reproduce their setup. For example, if their experiments might be reproducible if only you had access to the space shuttle, which doesn't exist. Things like that would be obvious, but there can be ones that are far more subtle where there's specialized equipment that might cause an experiment, if you wanted to repeat it, to be prohibitively expensive. If it's going to take you, if it took Google on all their computers 3 weeks to compute results, you might need to think about, well, how long would it take you on your computer, which might be 4 years, and that's not something you're going to do. Are there confounding factors in the way the data was collected or the experiments were analyzed that again make it impractical for you to be able to replicate or deal with their results? In their comparisons, did they use an unrealistic or artificial benchmarks? People want to show, this is especially true on problems that are new problems, so there's not a known state of the art, and then they sometimes make up an artificial benchmark and they didn't actually test an obvious competitive algorithm that should have been done. Are they comparing apples and oranges? Are they comparing CPU times on a Pentium, original Pentium class processor, or Pentium 3 maybe, or Pentium 4 versus an i7, right? Comparing times on two different machines is apples and oranges. You can't relate the two of them. How do you normalize the data across two different kinds of performances if they have them? Are there any methodological misunderstandings in the paper where they assumed that one uses this tool this way, and that's just not how the tool is done? Obviously, that kind of thing means you have a deeper understanding of methodological issues that can be applied. As you get more experience, that'll become easier, and you'll be surprised again. Sometimes people just mess that one up. Do the numbers add up? It is depressing how many papers I read where in one place they'll have one set of numbers where we ran this many subjects through, and maybe it's 100, and in another the numbers add up to 30, and there's a huge discrepancy, and you can't figure out why, or you can figure out why, but it really means it degrades the quality of the paper because the numbers aren't consistent in different places. Are their generalizations valid? Very often people will talk about it and have a general large-scale problem, but then they test on a small subset. So again, if they're talking human factors, and they talk about this general issue, but then they test it on 20 to 23-year-old college males because that's what dominated their test set, then they may not generalize at all, and they're not going to get very far. And related to that, are the claims modest? In my view, as you're doing the science, you want to make sure that your claims are consistent with your experiments. If people are too boastful, then you might want to question in broader everything they're saying, because clearly they're not being very pure about their science. They're trying to market it at a grand level. And there's a balance you have to do. People are allowed to market and make some broad claims if the data supports it. So you don't want to just instantly cut them off, but check that their claims are generalizably valid and the claims are modest enough to meet with what their data has. So that's the third phase. And I know I went through lots of questions. Not all of those questions will apply. In fact, on general, lots of them won't apply, but they give you some things to be thinking about. I don't expect you, as you do your critical reads in this class, for you to answer every one of those questions. I expect you to answer some of those questions that sort of come up to you as you're doing the reading, ways of questioning and looking at things. different critical questions will result in different kinds of answers as you're reading through the paper. So the next path, what I call the creative read, this is the fourth pass. I don't do this until I've decided that the critical pass was successful in the sense that while there might be some small issues with the paper, it's good overall. So the fourth read is to read creatively. At one level, I find reading a paper critically is easy in that it is generally easier to tear something down than it is to build it up. On the other hand, you don't want to build on a shaky foundation, so there's no point in reading too creatively papers that are bad and have lots of flaws. Although sometimes you'll find ways to be creative and fix their problems, which can still be useful. So I don't instantly throw away a paper that has problems, but I'm a little more careful about going on for the creative read. Reading creatively is harder. It involves more positive but also more creative thinking. It's a little bit harder to tell you exactly how to do this because it becomes more and more problem specific. But you want to start with sort of what's the novelty of the paper. A good paper will tell you what was novel, and if you sort of take that as the beginning, what new things can you do? What new directions does that open up that you can build on? Okay, and this is something that I'm suggesting when you do the creative read, you actually take notes on this. Literally write down, here's what the stated novelty. Spend 2, 5, 10 minutes thinking about what new directions it opens up. It's not quick, it's not easy. It's often staring at a blank page for a little while saying, wow, what could I do with this that I couldn't do before? And trying to come up with creative ways of using it in new directions. Okay? It might result in nothing. It might resolve with lots of really cool ideas what you can do next. The next question you want to do in your creative read is, what are the good ideas in the paper? They may not be what they claim as the novelty. There might be a technique they use in their paper that might have other applications or extensions that the authors might not have thought of. Can they be generalized further? Can they be applied to other problems? So not everything is what was novel. Sometimes it's novel to you. You didn't know about that technique. You didn't see it. If the authors have imported a technique from one field into another to solve their novel problem, maybe that same technique could be imported to solve other problems. So you want to think about what are the other applications. So to go along with that, thinking about what are the assumptions that went into it and what other problems share those assumptions. And that would allow you to generalize it. Okay? The next one is actually a little bit easier because could their ideas combine with other approaches, more importantly combine with your work? So as you're going through that, sometimes you're looking for new problems, which is what we just talked about. Here you're talking about, are there ideas that will let you solve your problem or be combined with your work that will let you do something new with your work or advance your dimension? Very often, this is the kind of result that people are off searching for when they do a search for papers. They're trying to figure out how to solve a problem, and that's perfectly fine. But if you start with a browse, you might not even recognize that you had a technique that this might be related to you solving it because you weren't looking for it. If there were other assumptions made in the paper, could those improve the approach? If you assumed the data was Gaussian and the noise was Gaussian, or if you assumed you could get this kind of measurement, could you do better? Could you ensure those assumptions are true for some subclass of problems? Would there be a measurement that would let you have data that they didn't use, but if you had that, you could simplify something or make something faster or more accurate? A minor direction is, are there better numerical methods than what they're doing? You'd be surprised how many papers are really taking a numerical method that somebody wasn't aware of and applying it to the same problem and the same technique and sometimes getting significantly better performance. So if I just did regular gradient descent, I might get stuck in local minima. If I did stochastic gradient descent or some other type of randomized search algorithm, maybe I can get something that gives me better performance. Or maybe if I use a method that's quadratically convergent instead of linearly convergent, I can make it faster. Lots of variations in terms of numerical methods. If you don't know what those are, that might be a class for you to look at during your PhD, is look for something in optimization or numeric methods. Are there possible improvements that might make an important practical difference? This is especially true if you're doing industrial research where what the paper had might be really interesting, but it's just not practical because maybe you can't run it on a mobile phone, or maybe you can't get the data in the form they want, but if you made some other variations, maybe there's some ways to make the differences so you can make the system very practical. And one of the things you want to do at the end of your creative read is to make sure that you're thinking, if I was going to do this, start doing research in this paper, what would be the next thing you do? Spend a couple of minutes thinking, what would I do if I was going to extend this paper? Put that in your notes. And again, I want to go back and reemphasize, right? Especially on the creative read, this is not a lot of reading. It's sort of looking at the paper, asking yourself some questions, and taking notes. Eventually, you may get good enough where you don't take notes if it's not your style. I'm not saying you have to, although for our journals, I'm going to make you do it. But you want to go through this. You want to be taking some notes when you first get started, and you'd be surprised. I still take notes on papers. I've been doing this for a long time. And one of the reasons I take notes on it is because I might be doing 5 or 6 papers in a row and I get them all muddled in my head, but also because there's so many ideas that you can have when you're doing this, you might forget them all. So making a note list or an idea list for each paper you read is generally a good thing. So this is the fourth path, the fourth path. The fifth path I don't actually have a slide on. We're not going to go too much into it in this class, although you'll probably do it for one, which is the in-depth. Okay, the critical read was about an hour. The creative read, in my view, is also probably around an hour. The in-depth read is unbounded. You could spend a week going deep into a paper. If you're going to try and implement it, and that's what we're talking about generally with in-depth, this is now a paper where you're going to try and build on it in some way. Your technique for doing that will be your own. It's really, how do I get there? The one thing I do want to point out is that if it's a paper, you also might want to check, can you get other versions of the papers? Maybe there's a thesis with more details. Maybe you can get their code from GitHub or write to the authors and get deeper. Once you're going to, I'm going to implement it, and you're going really deep, the amount of time depends on how deep and how clear was the paper, what is it going to take for you to implement it. So let's now go on to our last element, which is our first reading assignment. So your assignment for this week is to describe your research direction. Apologize for the typo. So you're going to go to your journal in Blackboard and you're going to describe your research direction. I'm looking for 2 to 3 sentences, maybe 5, sort of saying, here's the direction I'm planning on doing research for this semester. If you don't have one, pick one for this week, and you can always change your ideas later. I want you to go through what we talked about for sort of how to search for papers. Based on what you did, I want you to go search for and try and find 3 good papers for your research. Describe your process, how you did that search and the results. You should also suggest at least 3 papers you rejected along the way and why they didn't make your good list. But this is keyword-based search, so this is out doing a search. I want you to scan those 3 or more papers and write 2 or 3 sentence summary of each. Then I want you to critically and creatively read the best one, and in your journal summarize the critical results and the creative results. Finally, I want you to analyze the papers you looked at and other resources to select a good venue or top conference or journal for your research. So this is something that if you were going to go, you're going to go read more papers or write more papers. Okay, and I want to put that in context. So I'm going to tell you what your next assignment is, which is due in 2 weeks, which is you're going to choose a top journal or conference based on some of that on your analysis. And now you're going to begin the large-scale process where you're going to browse at least 30 papers. And you're not to search for papers or titles with keywords. You're just going to search for the conference or journal title. Once you know what that conference or journal is, you're going to go through, say, the first 30 papers in it. You're going to browse those 30 papers, and I want you to time yourself on each. Aim for no more than 2 minutes for the browse. Then you're going to whittle that down to a list of at most 6 or around 6. And you're going to write the 2 or 3 sentence summary, and then you're going to critically read the 2 or 3 best, and you're going to upload your notes. For both this week and for this assignment 2, handwritten pictures pictures from your phone of handwritten stuff is actually up okay. I just want to see that you're actually doing the work and taking some notes, not just trying to sort of muddle your way through and hope all of this works. In week 3, when we come to class, you are to be ready to discuss the process and your learning. Not really want to discuss the papers in details. I want to think about what you did in the process. So you're going to actually have 2 weeks, and I just want to put these out now so you can sort of see the juxtaposition. In week 1, you're going to do just search. I don't want you to browse. And then in week 2, you're going to do a browse, and we'll talk a little bit about what you learned out of the 2 processes. So that's it for our first week of Computer Science 6000, Computer Science Research Methods. Hopefully these videos have given you some good background, and you can move forward with the beginning of your research journey by searching for some relevant papers.